Hi, my name is Vahan Davudyan. I'm a physics experimentalist for 30 years. First of all, I'd like to thank so many people emailed me. I even had a comment, and that is so encouraging. That is the best feedback for me, and I appreciate that. And from now on, I will try more and more, get more theories and then be more precise, and I appreciate that. Thanks a lot. And today our topic is radioactivity, which is so important in our life. So it's Radiation and Radioactivity by Vahan Davudyan, physics experimentalist, and this is my email, vahandavudyan@aol.com. So this is going to be so comprehensive, and I'm hoping that you guys will love it because I covered almost everything. Because nuclear physics is not easy; it's very complicated. But I tried to cover almost everything, the basics, and I'm hoping that while I go through, I will explain step by step what do I mean by radiation, radioactivity, and things like that. So it's amazing. You must have heard about the uranium, which is so important. And you can see in this, this is called like a stairs, and then you can see uranium 238, and then goes all the way. You can see what you can see here, the mass of the atomic limits are reducing. See, 238, 234, and comes to 230 and 226, 222, 218, 214, all the way to 206. And in fact, 206 is the lead, but that is the end of the line. So in other words, this is where everything stops, and the 206 is a lead which is stable. So this is not, radioactive anyway. And in fact, we have like a alpha decay and beta decay, and this was named by Ernest Rutherford, the New Zealand physicist. He was great, and then he explained everything. And in fact, alpha, beta, and gamma are the words from the Greeks, and that's what they name it. So I will explain as we go through, and they have the half-life, and then they have a alpha decay and the beta decay. I will explain everything, but before I start this, I have to give you the introduction, because it's so important when we're talking about the radioactivity. It's also chemistry involved, so I have to let you know about the Earth's structure and the role of radioactive in Earth, how they make Earth hot always, and then everything else, and even the sun, and then where do the element come from. I have to explain that. So before I start this, let me give you this introduction, and we can start this later. Let me take this off first. And this is the introduction, so you can see exactly what we need to cover, because it's so important that you have some exposure that what do we mean by radioactive things. So this is introduction. First of all, evolution of the atomic theory, and this is so important that you know what. Where does it start? If you don't know the atomic structure, you won't be able to visualize how the radioactivity works, because you're dealing with the neutron, protons, electrons, and then alpha decay and beta decay. And in fact, this started with Mr. Dalton, English physicist. He was great scientist, and in fact, he used some balls, wooden balls like atoms. But at that time, atomic theory was just getting shape. So in other words, it was developing, and he was fantastic scientist. That was way before J.J. Thomson and Ernest Rutherford, and then Marie Curie, and then Henry Becquerel and everyone else. But he, his idea was so good that why the water is always H2O. Methane is CH4, and then ammonia is NH3, and ClNa, for the salt. And then for the water, he scrutinized and scrutinized, and finally he knew that, this proportion is always the same. So what is the secret behind the formula for the water H2O? And then he started this, and that was amazing. Before him, they had no idea what the atom was, and then after him, J.J. Thomson came in, and then he discovered the electron. That was breakthrough in science, and then some people were so amazed, we can't even, accept the theory of atom. Now he's talking about subatomic particles, like electrons. But that's what happened, and gradually I will explain what happened. So this was J.J. Thomson for, electron, and then for the proton was Ernest Marsden, Hans Geiger, and Rutherford, and for the neutron was James Chadwick, and then Niels Bohr for the model of atom, and then electron shells. And you know what? Atomic structure is so important. And then while we go through, I will explain that why, in decaying, sometimes, the neutron becomes proton. And then the mass changes, and then the atomic number changes, and everything else. And then I also will explain, radioactive elements inside the earth, and then the sun's structure, because if you don't know the sun's structure, how do they do when they explode, when they run out of hydrogen, what will happen? All these things in our body, calcium, sodium, potassium, you name it, they came from stars, but I have to explain a little bit where do they come from. And scientists developing radioactivity was Henry Becquerel, then Pierre and Marie Curie, wife and husband, and Ernest Rutherford. And then this was a Russian scientist, his name was George Gamow. And then you can see how important it is. I mean, this is amazing. I mean, it works so good. I mean, the radioactivity, there is no doubt. I mean, the precision is unbelievable. And why the neutrons have no charge? And then I will explain the role of, like our sun is not supernova. It's just fusing hydrogen, and then we get helium, and then the energy. But, I will explain the supernovas, that what happened, those are at least 5 or 10 times more mass and larger than our sun. These are the scientists, their contribution to radioactivity was so, amazing, and I will tell you exactly. This started with the French scientist Henry Becquerel, and he was so lucky. He was born in a scientist, family, and then he was so good. He went to Polytechnic in Paris, and then he graduated, and his main, major was phosphorescence, and then the light, and then everything about the light. And then he was so good at that, and then he got a uranium ore, and then because that was his major, he had no idea about the radioactivity anyway, so he put radioactive ore, with the photographic paper under the sun. And then he was thinking that, if he put that under the sun, what will happen? It will have a trace on that photographic paper. So he did this over and over again, and nothing happened. And he had no idea what was happening. Anyway, I could say he maybe did this experiment for, more than a year, and then there was no result whatsoever. So what happened one time, he just was almost about to give up this experiment. Then the weather turned so bad, and it was like a storm, and it was so bad, there was no more sunshine. So he decided to put that uranium ore and everything else with photographic paper, and then wrap it and then put it in a dark room in a drawer, and because there was no sunshine. After a week, he came back. Then he saw this. You can see these pictures. This is the, and then after a week, he came back. He realized that what happened, that, uranium has a mysterious, rays that, is exposing these things. And you can see they expose this photographic paper. And then from then on, he realized this is not X-ray. This is nothing like, phosphorescence. But let me explain what a phosphorescence is. And you must have heard, even in high school, when the light hits phosphorus things, well, their electrons are going to jump into higher electron shells. And then when they drop down, Niels Bohr theory, you know that, then they are emitting electron. But phosphorescence is a little bit different than fluorescence, because fluorescence immediately they just emit light, but the phosphorescence is a little bit delay. And if you recall, in my a month ago we were talking about Mr. like X-ray, discovery of X-ray, and TVs, the old TVs and the monitors, like it's been discontinued like 20 years almost. So inside the screen with the CRT, they had phosphorus, and that would emit light, and then you could see A, B, C, D, or whatever. But now they don't do that anymore. Now we use a new technology. And this was in 1896. Then that is amazing. After this, and Marie Curie and the husband Pierre Curie, they were in same city, and then they followed everything, and finally they got Nobel Prize. They shared all in 1902. Then what happened? Marie Curie was amazing scientist. She was so dedicated. I have never seen women with this great extraordinary determination, to discover these things. So anyway, they got two Nobel. She got two Nobel Prize, and then even in 1911, she got another Nobel Prize for the, radium. And radium is so violent, is also radioactive. But I was thinking about her dedication, how good she was in science, and then she would never give up. And there was a uranium ore called pitch blende, and then she realized that is 300 times more, has more radioactive than the uranium ore. And then this was called pitch blende, and then she probably had tons of pitch blende. And then I remember I saw the one science movie. She was blending that, extracting all day long, sometimes 12, 14 hours a day. How difficult it is for women, that hard work. But that dedication and that determination finally paid off. And then she discovered the polonium, because she was from Poland anyway, so they named that polonium. And in 1911 again, she got the Nobel Prize for radium. And that was amazing. That changed everything. And in fact, radium was so good, when they put it in, like anywhere, so that would conduct electricity. Because, I have to explain, radioactive material, the ionization is unbelievable, it's the best. So that's why Marie Curie realized, whenever they're present anyway, it looks like the air is not, insulator anymore. Earth is air is like a conductor. So that radiation is ionizing the, air, and then you can have electricity. She also coined the term radioactivity. And then after them, and this is so amazing, I want you to know about this. In 1902, after, she blended and then extracted tons of pitch blende, and guess what? She extracted 1/10 of the gram of the radium. Can you believe how difficult that job was? I mean, 1/10 of a gram, but you know what? It was radioactive, and then she got Nobel Prize for that. And in 1908, another genius came around. His name was Ernest Rutherford from New Zealand, and he was also so good. And then he discovered protons, and then he discovered that it's called spontaneous disintegration of atoms, and that was his idea. And it looks like, sometimes I think about this word which is so good. I love this word, intrinsic. Intrinsic means sometimes things are, in some, element, some material. It's just naturally is there. Like, when we're talking about something is moving, kinetic energy is already there. But if you have no motion, kinetic energy is not there. And this was exactly what Mr. Rutherford. This integration of the atomic nuclei is called, radioactivity. And then he was so good, and then he got, Nobel Prize also. And then he was the only scientist that this was great, idea. This was breakthrough in science. He said, you know what, we can use this radioactivity because it's like a clock. And we can use this to calculate how old our Earth is. Well, I will explain as we get to the next posters, and then you can see exactly what he was right. And this idea was, a groundbreaking idea. It was so good, and then it worked out. Okay. First of all, I have to explain about alpha decay and the beta decay. It's so important because when you have something like uranium, and like I said a few minutes ago, it's spontaneous, and the whole atom is not getting disintegrated. It's gradual, and that's why we have the half-life and things. Gradually, atom by atom, they're getting decayed, and then what happens? Is exactly like our sun. The mass is getting less because whenever you have alpha decay or beta decay. So in alpha decay, you can see here we have 2 protons and 2 neutrons. So what happened? The mass of the atom, whatever that radioactive is reduced by 4, but the atomic number is increased by 2. And when we're talking about beta is different because the neutron is automatically transforming to proton. And then what happened? The atomic number goes up, and here we have like the electron is emitted. This is so important that we have to know that how do they determine the half-life. I will explain it over here. See, imagine if the half-life is like 8 days, right? When the 50% sample is left, and then another 50% will be in 16 days, it'll be 25%, and then it goes up and down, down, all the way. Some of this, limit you cannot believe. Some of them, like this first one, which is uranium-238, is 4.47 billion years, the half-life. And some of them are milliseconds. Let me see which one I can find. Yeah, like this one here. Polonium is 0.016 millisecond. You see how, and some of them are like this one here is 3.1 minutes. Let me see what this one is. This one is lead, yeah. So what happened? This half-life is the indication that how much of this radioactive element is decayed. And in fact, this is so important that it is showing the penetration. And then when we have alpha particles, the paper, ordinary paper can stop this. Beta particles, this has to be, like a cardboard, or I would say, metal will stop it, but gamma is no way. This is the only way. You have to have lead, like, at least 5 or 6 centimeters lead, thick lead will stop it. Sometimes when you go to dentist, you can see that heavy jacket you're wearing. That is nothing but the lead, because X-ray is so energetic. They can damage the good cells, so they put the jacket on you, and then they do everything. And here you can see all this uranium-238 goes all the way down to, like I said a few minutes ago, it goes all the way to 206 lead, which is stable. But you can see this is a step by step. It takes billions of years. This is the way they, calculated the Earth is 4.6 billion years old. And in fact, I have to explain one more thing here. C-238, you cannot use this for atomic bomb because you have to get 235. But the point is, 235 is not natural, because this you can find in HR 238, plenty, not plenty, I mean you can find in so many places, but 238 is so difficult, and then the process is so difficult. I mean, you have to be so careful, and it takes a real long time, and then you have to enrich it, and God knows, probably you get less than few tenth of the gram, 235, and then that is fissionable, and they can do atomic bomb anyway. And this is amazing story for the Hans Geiger, and because you know about this Hans Geiger, he was German scientist, and he used to work with Ernest Rutherford, and then he invented this. And what this is measuring the radiation. And well, I have to explain a little bit, and then talk about the other scientists. Inert gases are so amazing, like argon, neon, krypton, xenon. If you go back to atomic structure, you can see how they are. They don't have extra electron like sodium or potassium or lithium that can easily be given away. They don't have it. Their orbit is so complete, and that's what they call it noble gases. And it's very difficult to get to react with the other elements. But you know what? Like I said a few minutes ago, radioactives are amazing at ionization. So this has a tube, and whenever there's a radioactive elements here, so what it does, that noble gases are ionized, and then they conduct a little bit electricity, and what happened, that electricity is enhanced, and you can tell that you have a radioactive element. But then shortcoming about this is it doesn't indicate, it does not specify that it is alpha, gamma, or beta, but it shows that there's a radiation. And this is amazing story, and sometimes I have to criticize some physics books, and they never mention that when the proton was discovered, that solved the whole thing. Everything was in atom it becomes so clear. And then before that, as you remember, J.J. Thomson says like a pudding, and then because he discovered the electron, but he had no idea. Everything was so fuzzy, and he had no idea how the atom works. But he had a hunch that beside the electron we have more things. So this is the story, and you may not believe that his name was Ernest Marsden, and then he initiated everything, and that's why Mr. Ernest Rutherford came up with the discovery of proton. But that was not his idea. That was Ernest Marsden. He was 20 years old, so he graduated in physics, and one day he walked in the Hans Geiger's office. Hans Geiger was also good experimentalist, and she said, I want to carry out one experiment. Hans Geiger said, what is it? I said, yeah, is for the atomic nuclei. They had no idea about the proton at that time. Hans Geiger was a good man. He said, well, I have to ask my boss, They spoke with, Rutherford, and then Rutherford, it's okay. So these two conducted that experiment, and that was so famous. It's called gold leaf experiment. And why did they choose gold? And then if you realize gold is so important in our life, that is the only element in our system, in our earth, is always occurring naturally. It is not compound or anything with the others, so you have to electrolysis and then separate them. Gold is amazing, and that is so malleable, and I don't know how they did it. This gold leaf they did in their experiment was probably 10 nanometer. That was so difficult. So they had that gold leaf, and then they put it in a round thing, and that round thing that was almost like 30 centimeters across. Then they coated with zinc sulfide. So anytime they had charged particle hitting, they would emit light. So they started with radium, and then the alpha particles. So what happened? They bombarded that leaf, and then what happened? Some of them were coming back. They were bouncing back. And then they immediately let Rutherford that this is what happened. Rutherford was an amazing physicist. He was also chemist. That was important because chemistry is so important in radioactivity. Rutherford said, yeah, this is why, because both have positive, and then they repel each other. Well, of course, not every thing was repelled. Some of them repelled. Anyway, Ernest Rutherford, he appreciated that, and then he said, I have to compensate that somehow. So practically, what happened? Proton was born, and then how could you believe 20 years of age, Mr. Ernest Marsden, English, graduate from, physics, become university professor. That's why, because Mr. Rutherford recommended him, and he became university professor. So I'm glad that happened. And then after that, Mr. Chadwick came, James Chadwick, neutron came in, and imagine how important the neutron was, because that was amazing. How difficult it is, because proton was easy to discover, not easy compared to neutron. Electron was easy to discover because they had charges. If you're talking about neutron, there is no charges, but that scientist, English scientist, James Chadwick, was so genius. He figured it out because neutron is playing important role in radioactivity. Like I said a few minutes ago, neutron can become spontaneously proton, and imagine that's the reason why neutron by itself cannot live, always had to stick to someone. And the neutron life, you may not believe, is only 15 minutes. But I will explain what happened inside the stars, what happened, when we have, like our star is not big enough for that purpose. But, the supernovas, some stars are 10 times, 5 times, 10 times larger, or, more massive our sun. So what happened, everything is, in nucleosynthesis is a factory for the elements. All this carbon, hydrogen, carbon and everything else, sodium, potassium, everything is, in that factory, is produced in that factory. So it goes all the way to iron and then it stops. And the iron is a little bit different, And then what happened when they produce iron, not in our stars, because our stars is not big enough. And when the iron is produced, then it stops. It stops, and then what happened? Iron is so different. It's getting energy from the sun. It's not like the others, it's just emitting energy back, but getting energy from the sun. And at the same time, everything when that supernova explodes, everything it just expelled in space, plus the neutrons, all those elements, all the way to gold, and then so many things. And the good thing about the neutron is like a glue. Is sticking to the other things. Like sometimes you have like after iron you got cobalt, you got nickel. So that neutron is getting inside the nucleus, and then getting more mass, and becoming all the way. So that's why. Well, of course, I have to mention also that, George Gamow, was amazing Russian scientist. He was genius. And then I remember, in Colorado, they have a huge tower, 9-story tower, named after him because he was a good scientist. He proposed in 1948 that, in universe, when this happened in the stars, then the fusion of the hydrogen and then helium, and then the whole universe, the temperature was set to 7 Kelvin. And of course, he did not get a Nobel Prize. Unfortunately, some people did not understand that at that time. And then after so many years, and two scientists in the United States, they discovered that cosmic background, they got Nobel Prize. And then George Gamow was right. But one thing he did not explain was, heavier element. And there was another genius called Fred Hoyle came in, and then he explained. And like I said, the protons are, ejected in space. And then we got the heavier elements, and then like all the way to 238. And here, like I said a few minutes ago, it's called the change of nuclear atoms accompanied by emission of radiation, because it's spontaneous. And it's so important that I have to mention we have two important sources of energies. One of them is our sun. Well, ultimate is sun. And well, I think if we have like 5 billion more years left, and then it's always we get the sun. And the sun so amazing. 600 million tons of energy is hydrogen is converted to helium every second in our sun. And guess what? Only 595, only 5 million of it is becoming like energy. It's becoming like, we have like I would say sunlight and then energy. That's why we live. This is the source of energy. And another source of energy is radioactive. Radioactivity is so important in our Earth. And imagine if there was no radioactive in our Earth, because of laws of thermodynamics, it would cool. I'm not sure how, but it would cool. And then when decided to get the age of Earth, and then Mr. William Thomson or Lord Kelvin was amazing scientist, but he made a big mistake, and then he said that the Earth is 200 to 400 million years old. And they were asking why, because they said this is the way it cools down, and then because when the Earth was formed 4.6 billion, so it was like a molten lava. So that's what happened. It just gradually cooled, and then he did not take the role of radioactivity in our Earth, and that's why always we have like potassium-40, which is radioactive. We have thorium-234. Then we have 238 uranium. So because of spontaneous disintegration of those atoms, we got heat. And imagine what would happen if we didn't have any heat in our Earth, so we didn't have gravity, because the Earth core is like a solid nickel and iron, and outer core is the molten, and that is causing convection, and we get the gravity on Earth. And imagine how important radioactivity is on our life, and that's why we get that energy. And another important thing about radioactivity is isotopes. Isotopes are amazing. I give you one example. Like potassium, we got 39 stable, and then potassium 40 is radioactive. And then the half-life, half-life of the 40 is 1.25 billion years old. And then imagine when those some nucleus like this, they have like this one has 39 proton and 39 neutron. But sometimes we have extra neutrons, and then it's not playing role at that time. But what happened? The mass is increasing, but their property is the same. The chemical properties is not changing, but you have extra things, and that makes a big difference. And sometimes if you get in a chemistry books, you can realize most of this, like iron has so many, potassium, uranium, all this, even ordinary elements, some of them have different isotopes. That's what happens. So that in chemical they're the same, but they have a more mass. So age of the Earth, I just explained few minutes ago, but Ernest Rutherford was so right about that thing, and finally they realized that they can get that from the zircon is amazing rock, and then they have found 4.4 billion years zircon. So Ernest Rutherford that we can do from the uranium-238 all the way to the lead-206, and then that process will tell us that Earth is 4.6 years old, 4 billion 6 years old. And then another American scientist came over, and he did more carefully. He was better. His name was let me read it for you. Let's see, Patterson. Yes, his name was Patterson, I think. I think his name was Cameron. His name was Claire Cameron Patterson. Then he said that we don't have to get the age of Earth from the rocks from the Earth, and then he was right, because they're contaminated. We have to get the meteorites, because they are exactly when the Earth was formed, they're left over. And he was right. And finally, Mr. Patterson came with 4.55 billion years old. And this is the latest idea that, the Earth is like that. And then we have like 4.55 billion years old for the Earth. And then I have to explain something that, his name was Socrates, and then his student, his name was Democritus. And imagine 2,400 years ago, how genius they were. They said, if you want to understand the universe, you have to understand the smallest particle. They had no idea what the particle was. That was the smallest particle of the, universe. And they came up with this word. It's called atomus, means uncuttable. That you cannot cut that any further. And that was amazing idea. How could they have this insight 2,400 years ago, that this atom exists. And now in 21st century we know that their insight was good, and then they had this. And then this was, I think, in 5th century. So atomus comes from atom comes from atomus, which is uncuttable. You cannot cut that any further. Well, of course, there are more things, and then I just don't want to take your time a lot. And then I'm hoping you guys love these videos. And then And the good thing about the radioactivity is it's just it's got so much explanation. Oh, I forgot something. When you go to chemistry book, and then you can see here like Al, this is for aluminum, and the number on top is the atomic number, which is the number of protons, and then the second one on the bottom is the mass. And then sometimes that says it's a relative atomic mass. The reason why I explained, because of different isotopes. Sometimes they have more neutrons, sometimes they have less neutrons, but you know what? That is the average, that 27 for the aluminum, which is the 27 the atomic mass. That is, can be less, can be more, but that atomic number is always the same. So you got 13, protons, in the nucleus. Well, of course, in a human body, it's so important. Oh, I'm sorry. I have to explain this. I have one more. I missed this one. This is important one. I missed this one. It's so important when we're talking about radioactivity. You should know about atomic structure. And then you can see here, I have one, it's a carbon. And then you can see those plus signs. Carbon is 6, so we've got 1, 2, 3, 4, 5, 6 protons. And the neutrons are red or pink. And you can see there's no charge on this. And neutron always has to stick to someone. Something to survive, and then you can see the electrons, and then you can see here there's no charge. It doesn't show any charges here. And if you ask yourself, where do the elements come from? What is their role in the human's body, animals and insects and everything else? I give you the best example: potassium and sodium. If you go back to their atomic structure, let me see if I can find one. Yeah, here. I have one over here. So you can see that extra electron on the here. So this is sodium and this is potassium. Both of them have the extra, in their, the shell, the last shell, see, extra electron, extra electron. And sodium and potassium is so important in our life. I mean, why do we have sodium and potassium? Could it be something else? No, because they're so reactive. What do we mean by reactive? So this sodium atom, the last, electron can leave immediately, ejected immediately, so that's why we're so reactive. And when we're talking about sodium chloride, sodium chloride or salt is so important. But the reason why we have that violent reaction is because sodium is getting one electron goes, so in other words, it's losing one electron, and then what happened? The chlorine, the last shell becomes complete, but the sodium also becomes complete. So in a human body, the electricity is so important. Well, it's not like the ordinary electricity, is the atoms and things like that. But you know what? That sodium and potassium in the human's body is so important. We get the nerve impulses. And imagine that's so important. It's like a pump is pumping, sodium out and then potassium in. So we get that electricity in our body, and all these things, neurons, billions of neurons and synapses are working with that. And you can see here, inside the supernovas, or even in our stars, what happened, four hydrogen are pushed together. We're talking about extreme heat, extreme, pressure. Ordinarily, two positive charges repel each other. But this is going to be different. The pressure is so, amazing, is beyond our imagination. So they fuse together, and then God knows, like I said a few minutes ago, 600 billion tons every second. That's a lot of energy. So that's what happened. And then you can see it's always steps here. After the helium, we have lithium. After that, we have beryllium. After that, we have boron, carbon, nitrogen, all the way to iron. And after the iron, because the neutron is ejected, in space, they stick to the other things, and then they get more and more and more. Sometimes, I have a good advice for the young generation. You have to ask yourself, if you don't know the atomic structure for the, I mean, atom, you won't be able to understand the, radioactivity. You have to know that. You have to know exactly how things work. And sometimes you ask yourself why they are using for Tesla, Toyota, Mazda, and the other electric cars, why they're using lithium. The reason why lithium has, three electrons, and one of them is the outer shell is exactly like sodium. It's extremely reactive. And guess what? They don't have 1.5 volts, like the, magnesium and the other, things. It's 3 volts. That's why it's amazing. Tesla car, they use that. Mazda and then Toyota and there's so many other electric cars, BMW, they use that. And you have to know why they use lithium. And lithium is so good. So, and this always, that is so important, that goes all the way to the end. And this is so important that you can see these steps. 238 goes all the way to 206 lead. And why lead is blocking the most important energetic and killer, I would say, radioactive element, like gamma rays, because it's so dense. See, imagine 206, their nucleus is so dense. It's not like ordinary things. So that's why they can stop this. And this is the Marie Curie and Pierre Curie in their lab. And imagine her dedication was so good in science, and unfortunately at those days, the safety was not a big concern, and then she would put everything at home, in the shelves, and the poor lady died at the age 68 from the leukemia, and even her daughter died from the same thing, but they got Nobel Prize also. Juliet, her name was, with the husband, but imagine those days the safety was not a big issue. And I saw a movie, documentary movie, after 120 years, when you go to a museum, especially at night, you can see a little bit, glow in the dark. Well, of course, it's not harmful for the humans, but you can see 120 years, radioactivity stays forever. It's not going to go away. So, but you know what? Like I said, it's bad and good, but we have to make sure that we are not exposed to radioactivity. But on Earth, we are taking advantage because our it's producing heat, is the source of energy for us. So I'm hoping you like this video. If you like it, you can give thumbs up and then subscribe it, and then I'm hoping every 2 weeks I will publish more videos. And then I appreciate maybe I couldn't cover everything because radioactivities, so I just don't want to take like 1 hour 2 hours, but I just cover the basics. So thanks a lot for watching and appreciate it.